All right, so we're going to continue with actually one of my favorite problems in optimization because, well, you'll see why a little bit later. So we want to look at a Coke can. It's got to hold 12 fluid ounces and be in the shape of a right circular cylinder. We want to come up with the dimensions of the can that will minimize the surface area. Now, why would we want to minimize the surface area? One argument might be that the cost of making the can is related to the surface area. If the metal is a uniform thickness, it's a hundredth of an inch thick, then maybe the amount of metal that goes into the can is going to be proportional to the surface area. And so if we minimize the surface area, we're going to be minimizing the cost at the same time. But surface area ends up being maybe a little easier to work with. So we're going to start with a normal picture. Since this thing is round, we're not going to look at things like length and width and height necessarily, but we will start talking about the radius of the can, and we will need a height of the can. So we'll go ahead and label those. Our primary equation, the thing we want to minimize, is going to be for surface area. Now our can is going to be really made up of three separate pieces. It's going to be made up of the top, so we need the area of the top of the can. It's going to be made up of the bottom, so we need the area of the bottom of the can, and it's going to be made up of this side piece, which we will have to figure out how to come up with the area for that as well. Now the top of our can, that's easy. It's a circle, and so the area is just pi r squared, and the same for the bottom of the can. But the side, if you imagine, say we cut the top of the can off, we cut the bottom of the can off, what we're going to be left with is a hollow tube. If we slice that tube, say down one edge, and unroll it, we're going to be left with a rectangle. And you could take, say, one of those golden toilet paper tubes that you're so very, very glad that you have, and just try sort of cutting that open, and you'll see pretty quickly that the area of the side is going to be a rectangle. The one side of the rectangle is going to be h, and the other side of the rectangle, if it's got to wrap all the way around this can, the length of that side is going to be the circumference of our circle. And the circumference of a circle, either pi times the diameter or 2 pi r, and we will multiply that by h. We'll simplify. We have a pi r squared plus another pi r squared is 2 pi r squared plus this 2 pi r h. So our primary equation, surface area, we have a formula for that now. The typical problem, of course, we want to make sure that we've got our primary equation in terms of just one variable. We can see that it's got two variables involved, and so that secondary equation, or constraint, is going to give us a relationship between r and h that we'll be able to take advantage of. And that's, as always, going to be where these numbers that are given in the problem are going to show up. That is, we're minimizing the surface area for a fixed volume. So the volume of our can has to be 12 fluid ounces. And the volume of all sorts of regularly shaped objects like a cylinder, we can think of as the area of the base just multiplied by the height. This works for all sorts of regular shapes, as long as the the top and the bottom have the same shape and the same size shape, we can do this for lots of different shapes. And in fact, one of the central problems in Calculus 2 is coming up with these kinds of volumes. So the area of the base is pi r squared, that's a circle, and then multiply that by the height. But now we run into a separate kind of problem. We can't just say solve this for h in terms of r and push that pi r squared over to the other side, because, well, what sorts of units would we expect r and h to be in? I've got just a normal, Dr. Pepper can sitting here, and it says 12 fluid ounces on the side, but again, that's not the kind of volume unit that we need. If we want to do things like multiply r's and h's together, we need to know how r and h are going to be measured, and a reasonable unit for those might be inches. I know the can, here on the side says that it is 355 milliliters. There's a nice easy conversion from milliliters to cubic centimeters, and we could use centimeters as our unit, but this is America, and we don't do that hippie communist nonsense metric system stuff here. So we're going to go with inches, and we need to know what is 12 fluid ounces in cubic inches. If radius is going to be in inches, then radius squared would be inches squared. If height is in inches, then multiply that by the radius squared and we'll get inches cubed. So we need cubic inches here. I looked up on Google, and Google said that that 12 fluid ounces is the same as 21.656 cubic inches. Our units on the left side of our equation match what the units are going to be on the right side, but the fluid ounces does not, and we won't be able to use that value. So 21.656 is equal to pi r squared h. We're going to solve for h in terms of r, so that h is 21.656 over pi r squared. We could solve for r in terms of h. The problem with doing that, and mathematically we're going to come out with the same radius and the same height at the end of the day. The problem with solving for r in terms of h is that I'm going to have to take a square root of both sides, and that's just going to clutter up our primary equation with radicals, and we would prefer to avoid that if possible. It's significantly simpler to work with h in terms of r. Now we're not going to divide the pi out here, and you'll see why in just a second. It's going to cancel with some stuff from our primary equation. We're going to plug that into the primary equation. We have surface area as 2 pi r squared plus 2 pi r h. That's 2 pi r squared plus 2 pi r times 21.656 over pi r squared. You can see here that the pi is going to cancel. One of those r's is going to cancel, and we will be left with 2 pi r squared plus 2 times 21.656 is 43.312 over r. That gives us our primary equation in terms of just a single variable. Now we can start thinking about how to apply calculus in order to come up with the best value, the optimum value for radius. How do we find these optimum values, these maximum or minimum values, or these values that maximize or minimize our function? I'm sorry, I do want to kind of say this right. We look for critical values of the derivative. Surface area, 2 pi r squared plus 41.312 over r. Another way to say that is 2 pi r squared plus 43.312 r to the negative 1. This is just algebra. We have used the rules of exponents to pull that r up out of the denominator and give it a negative exponent. This step is not finding the derivative. It is making our function into a more convenient form that we can apply the power rule. Now find the derivative. Surface area prime is going to be, the derivative of 2 pi r squared is 4 pi r. The derivative of 43.312 r to the negative 1 is going to be negative 43.312 r to the negative 2. Another way to say that using the rules of exponents in algebra is 4 pi r minus 43.312 over r squared. Now, just as in our example where we talked about minimizing the perimeter with a fixed area, we do have a critical value at r equals 0. Unfortunately, that's going to make a can of 0 radius and essentially infinite height, which is not going to be very practical. That's not the normal kind of shape that we're used to working with. And so we're going to assume that r is not 0. We're going to ignore that critical value, and we will just set this whole thing equal to 0. Add that 43.312 over r squared to both sides, and we get 4 pi r is equal to 43.312 over r squared. We'll multiply both sides by r squared to get it up out of the denominator, and we have 4 pi r cubed equals 43.312. Divide by 4 pi. We get r cubed is 43.312 over 4 pi. Ask my handy-dandy calculator that I went out and found. 43.312 divided by 4 pi. And I get 3.4467. Approximately. We'll take the cube root of both sides, and that gives us an r of, let me find the cube root of that. And I get an r of about 1.51 inches. Now, we need to prove this minimizes our surface area. The second derivative test says that we're going to find SA double prime of 1.51, and we would like that, if we have a minimum, we would like that to be positive. Go back up to SA prime, and we can find that SA double prime is 4 pi, now plus 86.624 r to the negative 3. That's 4 pi plus 86.624 over r cubed. 4 pi is a positive number. 86 is a positive number. If radius is positive, which it is, then I'm dividing that by a positive number. That is a positive number plus a positive number divided by a positive number. And that has no choice but to be positive. I don't actually care how positive it is. All I care is that it's going to turn out to be positive. So r equals 1.51 inches is the best radius for our can. What is h? Well, our secondary equation from earlier says that h is 21.656 divided by pi r squared. I put that into my calculator and I find out that h is approximately 3.02 inches. So we found the best values, the dimensions of the can, that will minimize the surface area. Okay. Now, I want to take this one just a little bit further than some of the others and consider the fact that I have cans sitting in front of me, and we've all had, Coke, Dr. Pepper, whatever you like to drink. We've all had that, out of a typical can. And if the height is 3.02 and the radius is 1.51, that tells us that the diameter is also 3.02 inches. That is, if we look at the can directly from the side, the the diameter is 3.02 inches, the height is 3.02 inches. The can should be square. It should look like a square from the side. And clearly, with the experience that we've got, the cans are not that shape. The cans are much taller than they are wide. And given that, why is that the case? Certainly Coke and Pepsi or whoever it is that you like to drink, they make billions of cans a day. They must have done this problem at some point. They hired some engineer back in, 1902 to design the best shape of this can in order, again, typically we would think in order to minimize the cost. And so why is the typical shape of a Coke can not this little squat square shape that the calculus says that it should be? And so let's go back just to the very beginning for a minute and look at our primary equation. One of the things I said at the very beginning of the video is that we're kind of assuming that the surface area is proportional to the actual cost. And what we really care about is less about minimizing the surface area and more about minimizing the cost of the can. And if we consider it from that perspective, and we look at our can here, we see that the top of the can, in comparison, say, to the bottom, is very different. The top of the can, it's got the pull tab, it's got the little piece that's cut out. And in fact, if you've ever watched canning, and you can get on YouTube and find videos of canning going on, the way that these cans are built is the side and the bottom is all one sort of piece of aluminum, and the top, the can is filled, and then the top is attached with a special machine. So it's its own piece. And so it's reasonable to assume that the side and the bottom of the can are considerably cheaper than the top of the can. And so we can accommodate that in our equation by maybe saying that the top of the can costs 3 times as much as the bottom of the can or the side of the can. And we will interpret that as 3 times the area. When we do that, of course, 3 pi r squared plus pi r squared is going to give us 4 pi r squared here. Our secondary equation is not going to change, though, but that coefficient is going to change. Our surface area equation now says that our primary equation is 4 pi r squared plus 43.312 over r, which means that our derivative is now 8 pi r minus 43.312 r to the negative 2. And when we propagate that change through our algebra, we get instead, let's see, we get instead a radius of not 1.51 inches, but about 1.2. My calculator says 1.1989. I'm going to round that off to 1.2 inches. The second derivative test, you can go through, a little bit of this algebra, but what you're going to find ultimately is that we still have positive numbers added to other positive numbers, which is positive, and our new radius of 1.2 really is the best radius that we can have. And that's going to change the height that we calculate from 3.02 to about 4.8 inches. And, if we think about that in terms of the can that we've got, that means, of course, the diameter is now 2.4 inches. The height is 4.8 inches. And our can really is about twice as tall as it is wide. If you go to the grocery store and look at, say, 12 packs that are stacked on their side, you could turn that 90 degrees, and instead of laying the can, having the can standing up, having the cans 2 by 2 laying down. And the edge of that, the short, small face of the 12 pack really is a square. And that would support the idea that it is, twice as tall as it is wide. You put two cans next to each other, and now you've got something that more closely resembles a square. Again, certainly Coke, Pepsi, Dr. Pepper, whoever has done this kind of analysis and has determined that when they make 1 billion cans a day, if they can make those cans even just a tiniest fraction of a penny cheaper, in the long run, that's going to save a considerable amount of money. So why is this can the shape that it is? Well, probably because when we look at it from a cost perspective, that top is much more expensive. We made just a little assumption, maybe it's 3 times more expensive than the rest of it, and that actually gives us a pretty good estimate of what the shape of our Coke can is going to be. We're going to continue our optimization. For Business Cal folks, we're going to look at some problems that involve money and revenue, cost and profit. The Calculus 1 folks, we're going to look at a few examples that involve trig, in addition to some of those money and finance types of problems, business types of applications. You Business Cal folks, you're also going to get some inventory management and inventory cost problems that are unique to the class. Those are going to take a little bit of time to develop, but we will continue with the next video. Thank you.